Anyway, I'll start again. So welcome to our fifth lecture in virtual mineralogy, or mineralogy done virtually, I guess is probably the better word. I'm glad you can hear me now, and there we go. So so we're going to talk today about crystallography and symmetry, and as I was saying, this is one of the more difficult topics in mineralogy to discuss, and I find even with second year students when I teach this, it takes them a long time for it to click in their brain. And to be honest, there's parts of crystallography that didn't even click in my brain until I started teaching it, because once you have to try and explain it to someone, that makes a big difference in your understanding of a subject. Like anything else, if you can watch soccer or watch football, but until you actually play it, you don't actually understand it. And the same is with crystallography and mineralogy. And symmetry is one of the more difficult ones because some people don't have a very good spatial viewing capabilities. So some people have a problem seeing 3D or imagining 3D, and that's not uncommon. And crystallography is kind of a 3D thing anyway, so it can be a difficult subject to tackle, but I'm going to try and do my best here. If you have questions as we go, just let me know. Just put them in the question and answers, and I'll try my best to explain them more. If there's terms or something that you want explained or clarified, just let me know. So I'm going to talk about crystallography and kind of explain some of what you need to know to understand the mineral's crystal structure, and then next week we'll actually take this a bit farther so you can understand how this relates to actual minerals. So crystallography is not only a mineralogy thing. If you're a chemist or you're a physicist or you're a material scientist, you deal with crystallography. No matter what solid you're dealing with that has long range order and even sometimes short range order, you have to understand what the crystal chemistry is, and in order to understand that, you have to understand the actual crystallography and symmetry of your material. So yeah, exactly. If you can't, until you can explain it to someone else, you don't understand it yourself. And I think a lot of scientists actually have that problem, because I mean, that's the nice thing about working in a museum, is that I'm constantly having to talk to people who are not experts in my field. And if I can't explain it to non-experts, if I can't explain it to, I take for instance my mom or my grandmother, then I'm not doing my job as a scientist. You should be able to take what you know at a high level and reduce it down to something that's more understandable by the general public. I think that is a sign of a good scientist. But anyway, as I digress, so I'm gonna just show you the definition I showed you a couple of weeks ago about what a mineral is, because there's one thing in here that's very important, and a mineral has a highly ordered atomic arrangement. And if it didn't have this, we wouldn't have to talk about crystallography, which maybe in the long run would be good. And somebody a couple of weeks ago asked the difference between short range and long range order. Short range order is something that only occurs, the symmetry only is relevant for small bits at a time in the structure. Like for instance, glass. If you take glass from your window pane, it's not perfectly homogeneous in terms of its structure. But if I take this quartz crystal, assuming that this is one crystal, and I analyze the structure here and I analyze the structure here, it's going to be identical. So that's what I mean by long range order. You can repeat the symmetry, you can repeat the chemistry over tens of thousands of angstroms unit cells, and then that's long range order. Short range order occurs in liquids, it occurs in gels or things and it occurs in solids too, but nature doesn't like short range order. Nature likes things to be very ordered and perfect, and not kind of funky in the way that its unit cells line up. That happens, but it will happen because there's been a defect introduced into it. So that highly ordered atomic arrangement is something that we're going to be looking at today. So where's the next slide? So crystallography, the word crystal is one of my absolute pet peeves, and it goes along with the idea of when people put on cereal boxes or in food that it contains, 28 essential vitamins and minerals. No, well, it doesn't contain minerals. It contains elements that, that your body needs, whether it's calcium or iron or whatever. The crystal's the same, kind of the same thing. What people say, they see a nice quote unquote crystal, something like this that's euhedral, and they say that's a crystal. Well, if I bash this up and I turn it into powder, it's still a crystal, because the term crystal actually only means it's a regular geometric solid that is partially entirely bound by crystal phases. So Rennie's just poking his head in. So if we look at any mineral is actually a crystal, just by definition, that it has a regular atomic arrangement and it's a geometric solid. Whether it has pretty crystal faces or not, it has nothing to do whether it's a crystal or not. They're all crystals. It's just an arrangement of atoms in 3D. So you can have a crystal of, I don't know, sulfur, or crystal of, I don't know, salt or something. It's all the same thing, whether it looks like an actual pretty crystal or not. So crystals can be the development of those actual faces, and we can talk about crystallization another time, but the development of these nice, perfect euhedral crystals is due to cooling time. If it's fast, there's no faces. If it has time to grow slowly, it has a lot of faces. The pressure and the space. If you have a crystal that has nice faces, it's obviously not grown and run into something else. It's been able to grow until it consumes all of the medium that it needs to grow, and it's not going to get interfered with by anything else growing beside it. So as soon as you have things that are growing beside it, you're not going to get perfect crystal faces. And I'm sure you guys all know this, and the best crystals are the ones that you find in pockets. So of course they have the space to actually grow, and they need the time and they need the pressure, the proper temperature to grow too. Somebody asked, does a molecule constitute short range order? No, not a molecule in itself. You need something that's kind of a larger, like not just one molecule. One molecule in itself, repeated in different ways, could be short range order. So just in terms of types of crystals, or the depth, what we use instead of saying we have crystals, anhedral, subhedral, and euhedral. You've probably all heard these terms. Anhedral basically means there's no crystal faces, so it's just a pile of goo, essentially, or rocks, or something that you probably don't want to collect as a mineral collector. Subhedral means there's some crystal faces, and some of the faces have been either broken off or impeded by growth of other crystals. And euhedral is a crystal that's bound entirely by faces. So this is, from a collecting point of view, this is what you want, something that has had the space to grow, not impeded by any other mineral, and looks nice and pretty, like what the general public would call a crystal. So crystallography is essentially the systematic study of the symmetry elements in a crystal. So it's a systematic study of all symmetry in any sort of geometric solid, basically, whether it's a mineral, whether it's a chemical that's made in the lab, whether it's steel, whether it's whatever. Okay, so we're going to be looking at the positions of each of these atoms. So the atoms are the ones, the balls, the polyhedra surrounding them, the oxygens. We're going to look at the placement of these different atoms and how they actually contribute to the crystallography. So this is actually the crystal structure of Cosnerite, paper I just submitted a couple weeks ago, and it's these blue octahedron here are zirconium. These are actually a phosphate group here, a phosphorus with 4 oxygens around it, and these big green things are potassiums. So symmetry is basically symmetry operation, or symmetry element is any sort of operation that leads to a repetition of an object. So the classic kind of example of this, if you want to think about it in 2D, is pick an Escher drawing, and you know, the ones with the fish that are all kind of rotated and repeating throughout the 2D graphic, not the ones with the weird ones with the stairs, but the ones that are more geometric. That's essentially a symmetry element. So there's something that is relating one fish to another, or one bird to another, in that diagram. And we can talk about exactly how that happens in 2D and 3D. So symmetry elements, they can be non-translational and they can be translational. So non-translational means that it's not going sideways or up and down. And translational means exactly the opposite, is there's actually some sort of translation translation across from one place to another. So we're going to talk about non-translational symmetry because it's the easiest one to deal with, and it basically can define every mineral that you're talking about. When we throw translational symmetry into things, well, just for example, if we only have non-translational symmetry, there's only 32 ways that non-translational symmetry can combine together to form different arrangements. If we throw in translational symmetry, we're dealing with 230. So it's much easier to deal with the 32, and then if you really want to get serious, move into the 230 after that. So we have three basic, what we call non-translational symmetry elements. So these are elements that are going to affect the molecules or the anionic groups or the cations in a mineral. So how the, say, carbonate groups in calcite are related to each other, how the silicate tetrahedra are related to each other, or the silica is related to each other, or the potassium in a feldspar, how those in each of the unit cells are related to each other in the structure. And these are all things that we have to know when we're actually describing a new mineral. We have to understand those elements and how all the atoms are related in order to understand the mineral as a whole. So we have three different ways you can translate something, or you can relate one object to another without doing a translation. So you can have symmetry with respect to a plane. So if you think of a 2D plane, you can have symmetry with respect to a line, so basically an axis, or you can have symmetry with respect to a point. So it's just thinking of one point and something's going to happen through that point. So if we look at symmetry with respect to a plane, it's basically reflection. So if you stand in the mirror and you do this with your hand, you're going to see a mirror image of your hand in the mirror, right? That's essentially what happens in a mineral. So if you have something here, say it's silicon, and this is the mirror plane here. Mirror planes we diagnose we designate as M. So here, this happy face is going to be mirrored across this plane here. If you think of it, it was like standing up. It's going to be mirrored to this. And the same thing, if this is a mirror plane, the vertical line here, it's going to be mirrored to this. And you can put mirror planes diagonals, you can put them on horizontals, it doesn't matter. When we start talking about different crystal systems, each of these lines will probably be an axis or some sort of a line between different types of axes. So you can see even if this mirror plane here, the M1 mirror plane, if we cut it down the smiley face, this half of the smiley face and this half of the smiley face are mirrored to each other. And the same thing here and here. And they're also mirrored across the plane. So we've actually got 4 mirror planes here that are contributing to taking one of these happy faces and creating 4 more. So we have these things called stereographic projections that we use to kind of visualize how something that's in 3D would look in 2D. So think of this as a half of a sphere. So take a ball. I don't have a ball here anyway. Take a ball and cut it through the equator. So this is the projection of the equator, basically, from that sphere. So anything that's closed means it's on. I really need a ball. How come I don't have a ball here at all? So anyway, anything that's solid is going to be on the top, on the northern hemisphere, and anything that's an open circle or open image like that is going to be on the bottom. And then this is the equator line here. So if we show a reflection or a mirror plane on a stereographic projection, we put it just across here. It could be here, it could be here, it could be any of them. It could actually be around the equator, and we would put it around the outside rim of that ball. That's why this is sometimes easier with something physical in your hand to show. So a mirror plane is always depicted as a solid thick line. So if we're going to draw this, I mean, then this is what I have my second year students do. I give them symmetry elements and I have them draw exactly. My voice cuts out when you circle things. I don't know why, but okay. So yeah, so this, if we put a mirror plane here, this this object here, whatever it may be, an atom, a molecule, if we mirror it, it's going to be mirrored down into the southern plane, the southern hemisphere down here. So it goes right across. It's not going 180 degrees, or sorry, 360 degrees. It's going on kind of 180 degrees from the top to the bottom. If we have symmetry with respect to rotation, basically we're going to take an axis. I do have a stick. We're going to take an axis and we're going to rotate things around it in various ways. So you can have any amount of rotation around a line, but there's certain numbers of rotations that are controlled by the symmetry and by the chemistry. So the object rotates around a line or an axis. So you can have rotation that's 360 degrees, obviously divided by n, where n is the multiplicity factor. It's just basically the number of times that the object is repeated in 360 degrees. So you could have 1, you could have 2, you could have 3, 4. You can't have 5. That doesn't work. And 6. And then anything after 6 is just a repetition of 1, 2, 3, 4, 6. So we have symbols, just like we have mirror planes. We have symbols for our different rotations. It's 360 degrees. There's no point. If you rotate something 360 degrees, it's going right back to where it began. 180 degrees is this weird little oval symbol. So it rotates 180 degrees. You reproduce a point there, rotate back 180 degrees, and it comes back to where it started. 120 is a triangle. 90 is a square, and 60 is a hexagon. So if we depict them on these stereographic projections. So again, the outside line is the equator, and the circle here is something, a silicon atom, whatever. So if we go 360 degrees, a one-fold rotation, it rotates right back to where it started. If we have a two-fold rotation, sorry, there should be a dot here. Oh, look, okay, didn't realize it was going to do that. If we have a two-fold rotation, it goes 180 degrees, and we wind up with 2 dots. Oops, if I can go back. We would have a dot here, the one that began, and then we have another dot here, which is the second one that's produced in a two-fold rotation. Three-fold rotation, so the same thing. If we start with this point here, say it's a silicon, and we have a three-fold rotation, we're going to go 120 degrees, we're going to produce another silicon right there, 120 degrees, produce another silicon, and back to where it started, which is the same silicon that we started with. So you wind up with 3 silicons, basically because there's a three-fold rotation there, okay? Same thing with 4-fold rotation, 1, 2, 3, 4, 90 degrees in between them. And they're all, you can see they're all on the same plane. They haven't rotated down into the different hemispheres. They're staying on that same flat plane. Oops, okay, that shouldn't be there, but let's see if I can move it out of the way. There. It's probably a bit better anyway. So 6-fold rotation, same thing. If you have 6-fold rotation in your mineral, you wind up with 6 of the same things with a 60-degree angle in between them. So the actual axis is pointing right down into the center of the diagram, down through the hexagon, and everything rotates around it on that plane. So you can see already as we start looking at these different rotations, how you can relate that back to a mineral. So if you think of something that has 6 faces, like quartz, or well, quartz is bad because it's trigonal, but apatite or something, a beryl, something that has 6 solid faces on the outside, you can see where that symmetry starts coming into play. Or something that has 4-fold symmetry like naturalite. Naturalite, when you look at it, is a square, right? And each of the 4 faces are identical. So there's 4 faces that have been rotated around that central axis, and you're duplicating them on every side. So it gets more complicated when you have other symmetry elements that start playing into just the rotation, but you can see where you can start building the symmetry and looking at the mineral. And this is what we do when we look at, when we take a mineral and look at it and try and describe it and say we don't know what it is. If we can look at the crystal faces and look at what the symmetry might be, we can start narrowing it down. So I can look at this quartz crystal and I'm pretty sure this is not triclinic or it's not cubic, just by looking at what the faces look like, what shape they are, what angles they're at. So the one thing is, why is there no full five-fold rotation? A five-fold rotation does actually exist in quasi-crystals and different other things, but not common. It's because it doesn't pack well. So if you think of wanting to put atoms together so that they minimize any sort of distortions, like these empty spaces here, or they minimize the energy of the crystal, five-fold rotations don't do that. You see five-fold rotations in flowers, so it does exist in nature, but in minerals, it's not one of those things that works very well. So we get six-fold rotation, and you can see the honeycomb shaped here, but five-fold rotation with a pentagon, not so much. So this is just what they look like if you were going to take take all different types of rotations here using a 6, just to show you what they'd look like. So rather than a dot, it shows you the direction too. So if this was, say, if it was a molecule or like a silicon tetrahedron that was going to be rotating around here, the points would have to remain the same as you go. You can't have, you can see that this 6 and this 6 are basically the same direction. This one hasn't flipped around and gone 180 degrees. They're all in the same direction, just rotating around this central point. So the last symmetry element that we're going to look at is an inversion. So an inversion is basically symmetry with respect to a point. So if you think of having one central point and you're just going to have an element here, it's going to go through that point, it's going to wind up on the other side. So it's not a mirror plane, but it brings something to the bottom but completely inverts it. So if we look at this triangle here, we see A, B, and C. B will go to B goes through the inversion point and becomes B prime. A goes through the inversion point and goes to A prime, and C goes to C prime when it goes to the inversion point. The difference is, if this was a mirror plane and we put a line through here and mirrored this to this, B and B prime would be the same, but this would be A prime and this would be C prime. So there's a difference, even though it can kind of look the same, it looks different. Where the atoms wind up are quite different between an inversion and a mirror plane. A rotoinversion, which gets a little bit complicated here, is when we put a rotation and an inversion together. So what we're going to do, if we have something in the top hemisphere, we're going to rotate it, say 90 degrees, and then we're going to invert it. So instead of it being here, it winds up being down here, even though we've just rotated. So we always do the rotation first and then the inversion. So if we rotate something, invert, then we can rotate that one, invert, rotate this one, invert. So you can see it goes top to bottom, top to bottom, top to bottom. And that's the way we get more complicated and more diverse symmetry in a mineral, is by combining these different symmetry elements. And if you start working on cubic minerals, this is where this all comes into play, because they're horribly complicated in terms of how many different symmetry elements are together. It's a lot easier to work on things that have low symmetry, like triclinic and monoclinic minerals. So a rotoinversion, we're going to take this here, this symbol, we're going to rotate it 360 degrees and then invert it. So basically it winds up on the bottom. So we rotate it 360 degrees, which is nowhere content, stop sharing. Sorry, I'm going to fix the content here. Okay, so yeah, I don't know if you saw the last slide. Sometimes this does really weird things. I'm gonna go back here. Okay. Change the slide, yes. So I've been changing the slide, it's just that when I put it back to, there we go. Okay, so as I showed, I'll go back to this one just in case I missed it. Sorry, it's I don't know why this is getting confusing. So those are the 3 types of rotation, or sorry, 5 types of rotations, and we'll move on to the inversion. So as I said, the inversion is inversion through a point. So it takes one point and then puts it through an inversion point and winds up on the other side. So if we take a triangle here, ABC, we put it through an inversion point. B to B prime is pretty simple. C to C prime will go through an inversion point and it winds up on a diagonal from where it was, and A to I prime too. And as I said, the difference between an inversion and a mirror plane, because if you put a mirror plane in here, if you didn't have the points labeled, this triangle and this triangle, the top and the bottom triangles would look the same. But because it's an inversion, instead, A and C prime here would be this would be A prime if it was a mirror plane. Instead it's C prime. So these points are different. So even though it kind of looks the same, if this was a mineral, these would be all different elements. And say this was a silicon, a potassium, and a titanium, which would be an odd combination, but let's just say that it wouldn't be the same down here between a mirror plane and an inversion. So we have to be very kind of careful when we look at an inversion and a mirror plane to see if there's any difference. Let's make sure it changes. Okay, so last one is a roto-inversion, and this is basically the most complicated part you can get in terms of a non-translational symmetry. So a roto-inversion is when we take a rotation and we invert it. So when we have a roto-inversion, we use the symbol bar 1. So you can see here bar 1, bar 2, bar 3, bar 4, and there's bar 6 is over on the side for some reason. So those are the symbols we would write in say a paper or something. If you're going to draw them out, these are the symbols here. A one-fold inversion, or a bar 1, is a rotation plus an inversion. So it's a 360-degree rotation plus an inversion, which is just an inversion. If we have bar 2, so if we rotate and then do an inversion, it's just a mirror plane. But then these get more complicated. 3-fold roto-inversion, 4-fold, and 6-fold roto-inversion. So a 6-fold, there's no equivalence for these, but a 6-fold roto-inversion is basically a 3-fold rotation and a mirror plane. So you have 3 points on top, and you'll have 3 points on the bottom. And this is essentially, if you looked at a scalenohedron of calcite, this is essentially what you have. You can put your 3 fingers on the top, the top crystal faces, and you can put 3 fingers on the bottom crystal faces, but they don't match up. They're offset a little bit. So if we have just a 1-fold roto-inversion, again, it's 360 degrees, and then it's going to be inversion through a point. So it basically just winds up going from the top all the way to the bottom. A 2-fold roto-inversion is just an inversion, a 180-degree rotation plus an inversion, and it winds up just being a mirror plane. If you think of the mirror plane being the whole surface, the whole equator. So it's going to be mirrored. It's going to rotate. This top point here is going to go 180 degrees, and then it's going to go down to the bottom. So you wind up with 2 points that are essentially, if you think about the sphere, one up here, one down here, and they're just a mirror plane. It's a mirror plane on the equator, so mirroring it through the equator. 3-fold roto-inversions get a little bit more difficult. As I said, the 3-fold is basically 3 at the top and 3 at the bottom. So you're going to take this point, you're going to rotate 120 degrees, which should bring you to here. but it doesn't stay there. It inverts through to the bottom. So you wind up with this point. And if you number them as you draw them, it makes a lot more sense. So even though this point is here, it's actually a mirror of, or it's actually an inversion from another point. So if we take this one, we rotate it 120 degrees, it goes here, invert it, and we wind up with, this is point number 3. We rotate this 120 degrees, invert it, it winds up down here, 4. Rotate this 120 degrees, it's still at the bottom, it inverts, comes up to the top, 5. Rotate this 180 degrees, stays at the top, inverts down to the bottom here, 0.5, and then, or 0.6, and then if we rotate that 120 degrees, invert it through the up to the top, we wind up back at the point we start at. So any time you have any sort of sorry, this should have a mark in the middle of it too. Anytime that you have one of these symmetry elements, you have to follow it through and produce atoms or produce molecules at every single point until you get back to the beginning one. That's how you wind up with all the atoms in that mineral. If you just did it once, so if I take this one, rotate 120 degrees in here, I'm only going to get 2 points, but you have to follow it all the way through to when you get back to the original point. And that way you're going to get all the atoms in that related to that symmetry element and not just a couple. Fourfold's the same, sorry. Fourfold is the same. This one rotates 90, inverts down to the bottom. This one rotates 90, inverts down up to the top, rotates, it's at the top, it has to invert to the bottom, and then if we rotate it again, it's at the bottom, and then it inverts up to the top back to the original one that we had. Exciting, right? Yeah, students love this. It's a lot better when you're actually drawing it out, and I can give you, if anybody is that keen, I can give you some exercises and you can see how it actually works on paper. I'm sure there's applications on the web there somewhere that you can look at this too. So the last one's the 6-fold roto inversion. So you can see you end up with 3 points, 3 points on top, 3 points on the bottom. But in this case, they all can't do this. In this case, they all line up. So if you're going to have crystal faces, you're going to have 3 on the top, 3 on the bottom that actually are lined up together, not offset 60 degrees, which is what happens in calcite. So if we combine all these types of reflections, all these rotations and inversions, we get 32 unique combinations, and we call these the 32 point groups. So if you want to describe any mineral, you can put it into one of these 32 point groups. If we want to get really more specific and understand all the translational symmetry and actually describe the mineral in full, we need to go that one step further and add translational symmetry, things like screw axes and glide planes, and then we wind up with 230 point groups or space groups. But for now, we're just going to deal with the 32 because that's a lot easier. So if we combine all these together, again, I said all the non-translational ones, if we ignore all the translational symmetry, we wind up with 32 point groups. And this is the only way that you can put a mineral structure together. So 32 point groups, point essentially refers to the fact that the symmetry operations leave one point unmoved. So like I was saying, in order to actually define that symmetry and decide where all the atoms are going to wind up, you have to wind up back at the point you started with. If you don't wind up back there, you haven't completed that symmetry element. And if you think you have, something that's got a lot of symmetry, like a cubic mineral, you have a lot of different symmetry elements to go through before you build that entire structure. So group is related to the mathematical theory of group, the group theory, which allows for all possible non-identical symmetry element combinations. So it basically means we can take those 32, all those symmetry elements, combine them, and we get 32 possible point groups in there. So it's group theory. If you study chemistry or physics, a lot of times they'll talk about group theory. So these are the 32 point groups that we are dealing with in the 6 crystal systems, and we'll talk about these in a minute. So We can have in the triclinic system, we have 2. In the monoclinic system, we have 1, 2, 3. And then as soon as we start adding more symmetry elements, we get higher symmetry and then more possibilities of different symmetry. So these monoclinic and triclinic minerals are really easy to do with. They only have a couple of different symmetry elements that are possible. But then when you start getting to things like the cubic system, you get into all these weird wonky space groups here. Like this is pyrite. Which one's pyrite? This one, I think. But this is fluorite here. Fluorite and halite, 4 over m, bar 3, 2 over m. That's a lot of symmetry to start putting very few atoms through. And hexagonal too can get very, very confusing. So what it means is no center is there's no center of symmetry. So there's no center of symmetry here. Here there's a center of symmetry. So it means things on the top and things on the bottom are probably the same. And you can see this in minerals. If you have a crystal, you can, if you look at if it has 2 terminations, you can look at the top and bottom. If they're the same, they probably have the center of symmetry. If they're not the same, like a tourmaline, then they don't have a center of symmetry. So we can take those drawings that we did and we can put those into what we call Hermann-Mauguin notation, and this is what we use for papers, for manuscripts, and actually writing them out rather than drawing all these stupid little stereographic projections. So Hermann-Mauguin notation basically takes the unit cell parameters and links them to what those symmetry elements could be. So for example, 2, 2, 2 basically means there's 3 two-fold axes. 2 over m means that there's a two-fold that has a mirror plane perpendicular to the two-fold. 4mm means there's a 4-fold axis, 4-fold rotation on one axis, and then mirror planes perpendicular to the other axes. And in order to understand this, you have to actually understand what a crystal system is. But just a few points before we go here. Rotational axes are always parallel to an axis. So if you're talking about a 6-fold rotation, it's always going to be parallel to the c-axis. Mirror planes are always perpendicular to that axis. And then we can take those and and combine those into what we call the 6 crystal systems. So the 6 crystal systems are essentially what you'll have heard more about if you'll hear it's triclinic or monoclinic, but in order to decide that, you have to know what the actual symmetry is. You can kind of tell from the outside of a crystal if you have good enough faces, but then you get things that are like monoclinic, pseudo-monoclinic. If you look at aragonite, for instance, you're not going to look at twinned aragonite crystals, those nice ones from Morocco, and say that it's orthorhombic. You'd probably say, if you weren't looking closely, you'd probably say that it was probably trigonal or hexagonal, but it's not. So the 6 crystal systems relate external form and internal symmetry to a set of 3 or 4 reference axes. So the number of axes is going to depend on the crystal system. Each of them have a different set of axes. So crystallographic axes is just an imaginary reference line that we're going to relate those symmetry elements to, and therefore relate the atoms and structure to. So we define crystal systems, triclinic, monoclinic, orthorhombic, by the relationship of their axes and also by their symmetry. So if we look at crystallographic axes, so we can have A, B, C, we can have A prime, A1, 2, 3 in terms of the cubic system, or C and A1 and A2 in terms of the orthorhombic or tetragonal system. An axis just represents the edge of a unit cell. So when you see minerals and it says a unit cell is 8.345 angstroms by 23.86 whatever angstroms, those are actually the lengths of the unit cell edges or the axes that are being used to define the crystal chemistry. So if you're looking at a mineral, all minerals are going to have a different cell. Within some, like a diopside will have, or a peroxide will have a cell that kind of isn't within a range of each other, but around the same. But each of these is going to be diagnostic for that mineral and based on its chemistry. So we measure crystallographic axes just like we do bond lengths in angstroms, and an angstrom is 1 to the 10 minus 10 meters. So quite small. Those crystallographic axes and the angles between them is what we're going to use to define the unit cell. So if we think, I like to tell, especially kids, like every kid has played with Legos of some sort, but a unit cell is basically a building block. So if we talk about the body, you know, your cells are building blocks and they're repeated all over and you get a body. In minerals, essentially, you're going to take one colored Lego block and repeat it over and over and over again, and you get a mineral. If you take a red and a yellow and a green Lego and you mix them all up, that's not a mineral anymore. That's something that's not homogeneous. Each of those Lego blocks, even though maybe they're the same size, they're a different color, so they're not going to be the same. But if you take all red Lego blocks that all have 3 holes in them or 6 holes in them, and you put them all together, that's exactly how we're going to build a mineral. And each of those little Lego blocks is the unit cell. So everything that you need to know about that mineral, whether it's the chemistry or the symmetry, is contained in that one Lego block, and we're just going to repeat it over and over and over billions of times to actually form the mineral. So all the chemistry and all the symmetry information is inside that Lego block, defined by the 3 axes, the angles between them, and the chemistry, the actual atoms that are in the mineral. So if we look at the 6 crystal systems, the cubic system, we're going to go from highest to lowest symmetry. And the cubic system, if you think of things like garnets or analseams that are very equant, or pyrite for that matter, things that are very equant, those are things that are cubic because all 3 axes are the same length. A1 is equal to A2 is equal to A3. And the actual angles between them are all 90 degrees. So basically you're creating a cube. So there's a good reason why things like fluorite come in cubes. There's a good reason why they come in octahedrons too, and well, split into octahedrons. But anything that's in the cubic system has all 3 angles that are the same length, all 3 axes that are the same length, and all 3 angles that are 90 degrees. So in this case, A1, 2, and 3, and alpha, beta, gamma are all 90 degrees. The point groups in the cubic system, which for some reason have gone off the page, I'll show you those in a minute. All point groups in the cubic system have 4 3-fold axes. So no matter what symmetry in the cubic system, that's the one diagnostic feature in the cubic system. They have there's 4 3-fold axes. So there's 4 axes around which there's a 3-fold rotation. And you'll see the term holohedral point group, and holohedral basically means it's the highest symmetry in that crystal system. So in this case, the highest symmetry here is 4 over m bar 3 2 over m. That's the highest symmetry you can get in the cubic system. So what does it mean? The notation for the cubic system, the first symbol is what happens around A1, 2, and 3. The second symbol is what happens on the diagonals. So if you have a cube and you go through the corners, you'll have 4 diagonals if you draw them out. And the third symbol is what happens on the 3 edges of the cube. So if you go from edge to edge on each side, there's 6 edges. So what's going to happen around those. So each of those parts, so basically you have 1, 2, 3, 7, and then 13 different symmetry elements happening in one crystal, and you have to define them all. So these are all going to be repeats of each other. These are the same, but it's going to cause the atoms inside there to be confined by a lot of different symmetry elements. So if we look at cubic system minerals, things like halite, fluorite, garnets, galena, things that you can easily tell are cubic because they have that very equant or in fact cube look to them. So these are the different crystal systems for the cubic system, or different point groups for the cubic system. As I said, this is 4 over m bar 3 2 over m. That's the highest symmetry, and each of the dots represents where those symmetry elements are. And these are the other ones here. So these stereographic projections, you can take each of these and spread them out a little bit more as well. And sorry, Cormac's snoring back there. And look at where you're going to place the atoms. So you can see go from highest to lowest symmetry within that group, and you can see it gets a little bit less complicated here, but these ones are quite a lot of symmetry to be putting elements through. So just some pretty mineral photos, because we probably haven't had enough of those yet. For a cubic system, garnets, of course, all nice and equant, analseams, and pyrite. Pyrite, even though it's cubic, it's not the highest highest point group, And you can see that if you take a pyrite cube, the striations on them aren't completely identical on either side. They're rotated in different ways. So it's not the highest cubic system or highest point group, but it's one of them. The tetragonal system, if you think of tetragonal minerals, things like naturalite, you know, they have square cross sections. So two of the axes are the same, A1 and A2, and they're not equal to C. So the C axis, we always put the C axis up. So if you look at a naturalite crystal and from going down, the crystal is going to go through that square termination at the top of the crystal. It goes on the length of the crystal. So that could be smaller or it could be longer than the 2A sites, or it's 2A axes. So A1 and A2, those two axes that are perpendicular to C, are the same. Well, if they're the same, it means that both sides, or the four sides of the crystal, have to be the same length. So you're going to wind up with a square cross section. The angles between them are still all 90. So we're not shifting anything from 90, like from the cubic system. So all we've done from the cubic system to tetragonal is we've made the C axis, we can have that be any length it wants to be. So there's lots of different point groups in the tetragonal system: 4 bar 4, 4 over m, 4, 2, 2. The highest one is 4 over m, 2 over m, 2 over m, which means it's 4-fold over a mirror, 2-fold over a mirror, and 2-fold over a mirror. So all of these, this crystal system itself is characterized by having a 4-fold axis, and that 4-fold axis is going to be down the C axis. So if you look down the length of any tetragonal crystal, it's going to be a 4-fold axis down there. So if we look at the Hermann-Mauguin notation, as I said, the first symbol is the 4, so that's where the 4-fold rotation is happening, and that's going to be down C. The second symbol, sorry, is what's happening along the two other axes, A1 and A2, and they're identical, so they have to be doing the same thing. And the third symbol is what's happening at 45 degrees from those. So if you take those two A1 and A2 axes and you rotate it 45 degrees in between the two axes, it's going to be what's happening down those two axes. Checking to see there's no questions. So, for example, if you look at things like Vesuvianite, cassiterite, zircon, these are things that have square cross sections. They may have kind of elaborate terminations, just because they've grown that way, and there are other symmetry elements that could cause those terminations. But for the most part, they have a very square, blockish looking crystal. So these are the point groups going from the lowest symmetry up to the highest. This is the highest symmetry here, 4 over m, 2 over m, 2 over m. And you can see it's pretty simple here, but then we get more complicated here. The ones in red are the ones in red are the two-fold axes here. So some examples: tetragonal minerals, naturalite obviously is one of the more common ones. These are both from Gilles Hainaut's collection from Saint Hilaire. Zircon, sorry, total brain fart. Zircon here, which you look down, and this side are the same length, and there's 90 degrees in between them. The C axis would be coming down through, oopsie, it's coming down through the top here. There's a little bit of a pinacoid, and it'll be going down through the center of the crystal. So if you think of it, you can take that, what looks like an octahedron, but is actually a bipyramid. You can take it and rotate it through this top, or can't point to it, this top of the crystal, and that would be C, and the other two axes are either, it depends on where you put them. Some people put them out the edge of the crystal, and most of us put it out the corners here. It doesn't really matter. It's hard. It's easier to keep track of if you put axes out the corners. Orthorhombic system, so we're dropping a little bit in symmetry, and now instead of having A1 and A2 and C, we're going to have A, B, and C. So none of the axes are going to be the same length, but still we have all of the angles between them that are 90 degrees. So it still means we wind up with fairly blocky crystals, no strange angles to the crystals like you see in like gypsum. Everything is going to be still at 90 degrees to each other. It's a fairly simple crystal system. There's only 3 point groups in it, 2, 2, 2, 2 mm, and 2 over m, 2 over m, 2 over m. This is the polyhedral one. And all these point groups are characterized by having 3 two-fold axes. So in all these cases, we're going to have two-fold axes around A, B, and C. So in the Herman-Maugen notation, we have the first symbol is A, the second symbol is B, and the third symbol is C. And a two-fold and a mirror plane is essentially the same thing, and a two-fold and a two-fold here. So we're going to have crystals that have different lengths of their axes, different lengths of the sides of the crystals if you look at it, but still very blocky and 90 degrees. So things like olivine, naturalite shouldn't be in here, enstatite, and ferrocolumbite. So this is a topaz crystal here, nice equine crystal, columbite here, and this is a olivine peridot crystal down here. So the monoclinic system is when we start deviating away from the angles, and in this case, A, B, and C don't have to be the same as each other, and the angles A is equal to gamma, which is equal to 90 degrees, but then we have something called a beta angle that's greater than 90 degrees. So this is the beta angle here. Alpha and gamma are the angles between A and B and C. Those are still going to be 90 degrees. And the beta angle here is going to be on an angle greater than 90 degrees. So if you think of a gypsum crystal, or you think of a pyroxene crystal and you look at the terminations, they're never just flat, they're always angled a little bit compared to the other sides of the crystals. That's what's happening. We're getting a beta angle here that is a unique angle, and it's going to be greater than 90 degrees and cause that kind of tilting in the crystals. So the monoclinic system, all of them have a two-fold axis or a mirror plane. There's not very many point groups in here, 2m and 2 over m. So fairly simple crystal system. You can see as we start getting in lower symmetry, the amount of options changes dramatically, and we can only have a limited amount of symmetry within them. So in the Herman-Maugen notation, the first symbol is related to what happens along B, because the beta angle is what's happening between C and sorry, the beta angle is between C and A, and the B axis is the angle or the axis that's perpendicular to that. So we consider the B axis unique, and the one that's all of the symmetry is going to happen around. So things like biotite, which is hard to see if you're looking at in crystal because they often look hexagonal, diopside and gypsum are some of the classic ones that will show you the monoclinic angles. So this is a diopside crystal here. You can see that's a beta angle. If you put the C axis all the way through the center, the beta angle is going to be the angle between that C and this plane here, so much greater than 90. Same thing with a spodumene crystal here. This is the C axis running the length of the crystal, and then the B axis would go through the crystal, and that's the beta angle. Oops, that's the beta angle here. And the same with the gypsum. This face here is being caused by the beta angle. So if we completely get rid of all symmetry, and sort of going over a couple minutes here, but we'll finish both crystal systems, last crystal systems before we sign off. If we completely get rid of all symmetry and all the rules, we have the triclinic system. So none of the axes are the same length, and none of the angles equal 90 degrees. So you can have 3 different lengths of axes and 3 different angles. So that completely gets rid of all symmetry, and the only thing possible is a one-fold rotation, which is nothing. You're just bringing the element back to where it started, or an inversion. So you can take that rotation and then invert it through an inversion point. So they don't have the only possible symmetry they have is a center of symmetry and inversion point. So things like microcline, kyanite, oakenite, those are typical strophyllite group minerals, are typical triclinic minerals. So this is a amazonite here. Often they'll have a lot more faces to them that don't seem to follow any symmetry. Kyanite's another one, and this is a niobium-kletzkite crystal group of crystals that Quentin sent me. So those are just the diagrams for the triclinic, monoclinic, and orthorhombic systems. hexagonal system is the one that gets a little bit more complicated. In this case, we have, because it's hexagonal, we're talking about 4 different axes. One of them is the C-axis, which again is always the one that's the length of the crystal, and then the 3 other axes define that hexagon. So the angles between A1, A2, and 3 are 120 degrees, and they're always going to be coplanar. So you can divide this into 2 different crystal systems, and some people consider them completely separate. They're not. They're just defined by either having a 3-fold or a 6-fold axis. So hexagonal and rhombohedral or trigonal. In the hexagonal subgroup, we have 1 6-fold axis, and in the rhombohedral subgroup, we have 1 3-fold axis. So whether that C-axis has a 3-fold rotation around it or a 6-fold rotation around it will cause it to be either hexagonal or rhombohedral. If you think of something like a beryl versus a calcite, or a beryl versus a tourmaline, for instance, they're both in the hexagonal system, but one is always going to have 3-sided terminations, the other has 6. So the Hermann-Mangan system for hexagonal is very close to what we have in the tetragonal system. C is the first symbol, A1, 2, and 3, the second symbol, and then the third symbol is 30 degrees from A1, 2, and 3 because that angle, the total angle of difference for the rotation is 60, and it's going to be the third symbol. So things like corundum, beryls, tourmalines, calcites are all in the hexagonal system. Whether they have a 3-fold or a 6-fold is another story. So just some examples, a nice pink beryl here. You can obviously see the 6-fold symmetry here. This is a shoral tourmaline, and you can see there's definite 3-fold rotation here. And then this is a calcite here that you can, it has 3-fold rotation on the top with an inversion. And those are the stereographic projections for the hexagonal point groups. And you can see they get a little bit complicated as you go up to the highest symmetry here, which is 6 over m, 2 over m, 2 over m, and this is kind of a funky one here. Bar 6 m2, which is basically 3 over m. Yeah, they get kind of interesting. So that's just a summary of the 32 point groups. And just to show you as a kind of last slides, this is what happens when we actually go to look at these things in the crystallography manuals. We have Allison is a cubic. Alcine's triclinic. Okay, I'm gonna have to look that up. Anyway, so these are what different point groups look like in the international crystallography tables. Here's the point group 222 or MMM, and these are the actual space groups here, P222 or FMMM, and the F and the P are just basically how the lattice is centered, and that's a little bit much to get into at this point in time. So here are the 2 simplest ones. So P1 and P bar 1. So that's point group bar 1 and point group 1, both triclinic, and you can see they're very simple symbols. But these elements here tell us what the atoms in the structure when we're actually looking at, when we're actually trying to calculate things and look at where atoms are. We have to calculate their actual position based on XYZ in the structure, and we use these symmetry operations here to define where the elements that we're looking at, where we're going to put them, and we have computer programs that we enter this into, and it does that. So, and I think that's it. So that's it for today. Sorry, that's a little fast, and sorry for the screw ups at the beginning. But if anybody has any questions, we can take them now, and then we can maybe talk about what you want to learn about in the next one as well. So any questions, you're welcome to put them up on the screen. So yeah, we can talk. I mentioned Miller indices a couple weeks ago, actually, but yeah, we could talk about those further as well. John says he needs an intro to an intro. Yeah. No, I didn't. David asked if there's if I talked about Miller indices. I didn't. I talked about it a couple weeks ago, but yeah, we can talk about. I can do a whole lecture just on Miller indices and how you get the. It's something that's actually a lot easier to do in person, but we can talk about how you use Miller indices to define faces and axes as well. You have to kind of go into reciprocal cells and understand that a bit as well. What's the way to contact me? So again, I'll put my email up on the main site. If you look under the questions and answers section, I put up my email address there. That's the easiest way to get in touch with me. So for next week, we can either do some more crystallography or whatever, but I also have a presentation that I gave to the group here in Ottawa about diamond mining in Russia, if you'd be interested in that too. So if you have specific interests, let me know. We can alternate between one more academic talk and one mineral location talk if you want, or we can do back-to-back crystallography talks or such. It's up to you. Okay. Yes, if there's no more questions, I'll end the live event. And if you have questions, other questions or comments or anything, as I said, my email's on the published question and answer site. If you want to get in touch with me, or you can call me or whatever. This is also a call out to any St. Hilaire collectors out there. If you have varieties of ansilite, calcioansilite, anything in that group, I'm sooner or later going to be starting a project on them, probably later this summer. So I'll be looking to hound you for different specimens to analyze from the different environments and different habits, different colors, whatever, just so we can get an idea of what they actually are. So if you have ansilite samples, get in touch with me. Okay, I know some of the main culprits here that I'll get in touch with, but if anybody else has interesting ones, please let me know. Okay, thank you everybody for tuning in again, and we'll see you next week, June 10th at noon again. Okay.